So make sure that the mode is in radian mode, and we are determining 0.5 minus pi. I like parentheses around the top, pi, multiplied by the square root of 3. Okay, I'll be okay now this time. And divide by 360. Whatever that is. But now I have to go back and change the mode to degree. So I'll change the mode to degree and determine sine. Come on, please. Wake up, wake up, wake up. Oh, don't do this to me. Okay. Ah, okay, you took it. So second and quit, and go to sine 29, and let's see how close we are. I hope you're happy, because this you can determine, this you can divide, but without a calculator, you will not be able to determine sine 29 degrees, no matter what you do. Are you happy with the approximation? 4 digits. Is this good? Okay, so that's calculus. Any questions? Any questions? Okay, let's look at another. You choose now. That one I made up. Now you can choose anything you want. So we have e to blah, blah, blah. We have 1.999 to the 4th power. We have anything else you want. Oops, nobody can see. So there are 4 problems here and 2 problems here at the bottom. Your choice. Page 255. So we want to apply what we just learned in any other problem you want to work on. Do I get to choose, or you want to choose? Which one? 24 it is. 24. Very good. So this is e raised to, is it negative? Yeah, you have just 1 0. 0.015, correct? Perfect. Okay. So as a refresher, what is the formula? F of x plus a little bit is approximately f of x plus a little bit of y, which is f prime of x dx. What do we need to identify? We need to identify the function. We need to identify x. We need to identify dx. And then we just need to put everything together. Let's identify the function first. Which function are we using here? Very good. E to the x. X must be something known, because otherwise, what's the point? Very close to negative 0.015. Of course. Absolutely. X is 0. How much is dx? But negative, right? Excellent. How much is f prime? That's our best friend, e to the x. Good. Let's put everything together now. So now this piece is this. So e to negative 0.015 is approximately not equal to, because we know we are using the derivative, so we are coming up with an approximation, not with the exact difference. For that change in x, we are approximating. Good. F of x. I have to write e raised to Excellent. Very good. Plus f prime of x, e raised to, excellent, times negative 0.015. So what do these equal to? Both of them. 1. So then this is 1 minus 0.015, which is 5890. Not even in your wildest dreams you would have ever thought to be able to approximate e to negative 0.015. Don't tell me, because I won't believe it. So then, let's go to, here it is, e raised to, in parentheses, negative 0.015. Don't tell me that you would have ever come up with 0.985 without a calculator, because I will not believe it. Would you agree? Good. Do we understand what we're trying to do? Do we understand the mechanism? We're approximating an actual change in a function using differentials. Any questions? Okay, we're not done with this section. I would like us to look at a word problem now. And we have the linear approximations, which I haven't even looked at yet. Okay. Well, let's look at 34. Let's read 34. Ready? Okay. It says the radius of a circular disk is given as 24 centimeters with a maximum error in measurement of 0.2. What is 0.2? Exactly. What is x? (24), of course. 24 is x, minor change, 0.2. Perfect. Use differentials to estimate the maximum error in the calculated area of the disk. Since it says estimate and use differentials, what would I determine? Not delta A, but the other one that approximates it. If it's not delta area, which is the exact area, what is the other one that we just looked at? dA. Right? Delta A is approximately dA. We are not asked to determine the exact change. We are asked to estimate. So we are using the derivative, which means we are not using delta A, we are determining dA. Okay, so let's work on this problem. Ready? 34. Page 255. Did I start it? I think I did. Yes, I did. Okay, ready? So, the radius of a circular disk is given as 24 centimeters. Maximum error, 0.2 centimeters. You already told me that this is dr in this case, or delta r. They are the same. Okay. Use differentials to estimate the maximum error in the calculated area of the disk. Now we have to remember how we calculate the area of a disk. The area of the disk is pi r squared. Agreed? Good. So we're asked to find dA. How do I find dA? Remember, this is like dy, or f prime of x dx. This is the formula for the differential, not the exact difference, but the differential using the derivative. That's why I think they put the two words together, derivative with difference, and they said differential instead of the exact difference. Good. So then, now what? dA equals 2 pi r. We cannot forget that. This is not the derivative. This dy is f prime of x times dx. So dA will be 2 pi r times dr. Please understand the difference between f prime of x and dy. They are not the same. F prime of x is the derivative of the function, but dy is the derivative of the function times dx. Okay, perfect. So then, what I have to do is plug in the numbers. I have everything. So then dA equals 2 times pi times 24 times 0.2, whatever that is. I will keep it exact. So I will keep the pi in there. It's up to you. You don't have to. So this is 48, 9.6, is it? Yes? Perfect. This was part A. We estimated what that 0.2 triggers in the area, but it's an estimate, right? We know it's pretty close because dx is tiny. It's not big, right? So delta dA is pretty close to delta A, the exact. Okay, part B. What is the relative error? Okay, let's talk about relative error. The relative error is always determined as a ratio. The change divided by the actual. It's a percentage of it, okay? It does not have measurement units. So the relative error will be, in this case, dA over A. So the exact the error created or triggered by 0.2 divided by the total area, the exact area. Not the exact change, but the exact area. So now the top, yes, we have the number, but I would like to show you something. 2 pi r dr divided by 2 pi, I'm sorry, not the 2. So these are the two formulas. The bottom is the area of the disk. The top is the formula for the differential. And when you simplify a pi with a pi, an r with an r, you will get twice dr over r. What does this mean? The relative error triggered by 0.2 error in the radius is twice the relative error in the radius. One more time. The relative error in the area is twice the relative error in the radius. And now we can determine the exact, which is 2.2 divided by 24, whatever that is. I'll simplify by 2.2 divided by 12. And I can approximate it and see what that is. It's 0.1 over what? Over 6. So approximately 0.0166. No measurement unit because the top is measured in centimeters squared. The bottom is measured in centimeters squared. So there is no measurement unit for relative error. And lastly, they are asking us what is the percentage error. Okay, no problem. I just say 1.66%. Change that into, so a 0.2 error in the radius creates a 1.66% error in the area. So bottom line, everything has consequences. Questions? Questions? Okay, let's also look at one more. Should we look at one more?
Yeah.
Perfect. I like this one with a cube. Let's read it. The edge of a cube was found to be 30 centimeters. What is that? X, right? Very good. With a possible error in measurement of 0.1. What is that? Delta x, also dx. Perfect. Use differentials to estimate the possible maximum possible error, relative error, and percentage error found in the volume of the cube and the surface area of the cube. So the error of 0.1 in the edge triggers an error in the volume and triggers an error in the surface area. Anything has consequences, right? So let's determine those. Please tell me what to write. So first, this is 33 on 255. And we are told that there is a 30 centimeters and there is a 0.1. And I'm waiting for you to tell me what they are again. What is 30? Good. What is 0.1? dx, also delta x. We're not using delta x because we're not asked to find the exact. I'll find an example in which we're asked to determine both in a minute. Okay. Use differentials to estimate the maximum possible error in the volume. Part A, volume, and part B, the surface area. All of them. So they want the maximum error possible, maximum possible error, and relative error and percentage error in the volume and then in the surface. So first of all, let's write the formulas for both. This is a cube. Very good. 6x squared. Very good. Awesome. So let's start with the volume. Since we're asked to estimate the maximum possible error, what will I have to find? It's an estimate. I will have to find dV. Very good. Awesome. What is dV? Remember, dV is not V prime. Careful. So this will be, so 3x squared times careful. So let's write the formula one more time. So if I have a function, I meant to write the function first. I already went straight to f prime. If I'm given a function and I'm asked to find dy, I have to write f prime of x dx because that's the variable in the problem or in the function. Same thing here. This is a function of x. So when I'm asked to find dv, I have the derivative of this, which is 3x squared, times dx. Is that clear? Perfect. So this is the approximate error triggered by this error in the edge of the cube. So this will be 3 times 30 squared times 0.1, whatever that is. Now let's determine the same thing for ds before we look at the relative error and the percentage error. So what is it? So this is 900 times 327. So is it 27 and 2 zeros? So this is 27. A measurement unit. Very good. Centimeter cube. Good. What about the second one? The approximate error. How do I write this? Yes? Very good. So this is 12 times 30 times 0.1. So 360 with 0.1 will be 36. And what is this? Measurement unit? Perfect. Now they want the relative error for both. How do we determine the relative error? It's the error over the exact. The error over the exact. So there was 900 times 3 is 2700. Yes, yes, I caught too many zeros. Thank you, thank you, thank you. Yes, and here, am I okay with this? I think so. Perfect. Good. So now with dv, I want to do the exact same thing we did before. So dv was 3x squared dx divided by v cubed. Just to see that this is 3 times dx over x. 3 times as much. So dx is 0.1. So 3 times 0.1 divided by 30. And the same thing with ds over s. And then we'll change it in a percentage. So 0.3. I got 0.01, right? No measurement unit because it's cubic centimeters over cubic centimeters. And this is 1%. So a 0.1 centimeter error, plus or minus, it doesn't matter, in the edge of a cube triggers a change in the volume of 1%. Same thing with the ds over s. So ds was 12x dx divided by 6x squared. So this is 2 dx over x. So it's twice as much. So this is 2 times 0.1 over 30, or 0.2 over 30, or 0.1 over 15. And how much is this? And I also need percent. I got 0.006666, 0.0066, and this changes into 0.66%. So a change or an error of 0.1 centimeter in the edge of a cube triggers a 0.6 or 0.7 roughly percent change in the surface area, but triggers a 1% change in the volume of the cube. And this was possible using differentials. Questions? Questions? Okay, now I would like us to determine and compare. Let's choose, and then we'll talk about linear approximations. Here we're asked compute delta y and dy for the given information. Here we're asked to find the differential dy. We've done this, but we can do it again. All the information is there. But I would like us to choose an example from delta y and dy, in which we are asked to determine for a particular function and the given information to see the difference between the exact delta y and the approximation dy of the change. So which one? Any preference? No preference? Then I would like to look at, maybe 21. 2 over x. So 21. Still page 255. And we are given y equals 2 over x equals 4, and delta x, which is the same with dx, is 1. They want us to find delta y. They want us to find dy. And that's it. Which of these two is always easier to determine? The delta y or the dy? Delta y requires, remember, f of x plus delta x minus f of x. The dy requires f prime of x dx. So this is always easier. That's why we use it to approximate that difference. So let's start with that. So dy, we know the derivative of 1 over x. There is a 2 in front. It doesn't matter, right? So this is the same with 2 times 1 over x. We know now the derivative, and I hope moving forward we remember it, is negative 1 over x squared. So this is negative 2 over x squared times dx. And I just have to plug in the numbers. Negative 2 over x squared is 16, times dx, which is 1. So this is negative 1 over 8. Or negative 0.125. Now, in order to find delta y, there is a lot more work. So this is the approximate, or the estimate. But finding delta y is a different story. Is f of x plus y, right? X plus dx, I'm sorry, which is 5, minus f of 4. F of 5 is 2 over 5, minus f of 4 is 2 over 4. I have to find the least common denominator, which is 20. I multiply this by 4, I multiply this by 5. So 8 minus 10 is negative 2 over 20, or negative 1 over 10, or negative 0.1. And this was a friendly function, but it could have been way, much worse. X could have been 0.001, and that would have been even messier to get the answer. So this is always what we prefer. This is way more work. Questions? Questions? Okay. Do we need more examples, or can we look at linear approximations? One more? Very good. Let's choose. We want to do anything else, like maybe 22? Okay, 22. Let's look at 22. 1 to 55. We're given y equals e to the x. We're given x equals 0. And we are given delta x, of course, equal to the x, which is 0.5. Same question. We're asked to find delta y, which is the exact and requires more work, and dy, which is the approximate or the estimate, which requires much less work. Ready? So let's start with dy. Anyone remembers the definition of dy? Yes, f prime of x dx, perfect. So this is dy, but e to the x prime is e to the x times dx. All I have to do, plug in 0, so it's e to 0 times 0.5, so it's 0.5. This is an approximation in the error of the function triggered by a change of 0.5 in x. But delta y, can anyone give us the formula for delta y? So it's f of x plus delta x minus f of x, yes? So this will be f of x is 0, delta x or dx is 0.5, minus f of 0. So this is e to 0.5 minus e to 0, which is 1. And now I have to approximate that. And let's see what we get. E raised to 0.5 and minus 1. I got 0.6065. So there is some sort of difference, right, of 0.1. Why? Because as you see, dx is not very tiny. Very tiny is 0.1 or 0.01. So this is, half a unit. So then there is some change, some error between the two. Is this better? Point 0.6? You got something else? Okay, what did I do? I didn't put parentheses or something? Oh, I put the negative at the top. See what I did? E raised to 0.5, but then I had to come down and put negative 1. Sorry about that. Indeed, my apologies. It's, yeah, that's why I don't trust this calculator. It doesn't do what I wanted it to do. My apologies, sorry. Indeed, 6, 4, 8, 7. Okay, that's even worse, right? Only because half a point is not a minor error. Very good. Is this okay? We feel better about it? Okay. So let's see what this linear approximations is all about. I know you missed this. I'm sorry, but it's all the same thing pretty much. So here is P, but now this is A, and this is f of A. So then the coordinates of P are A, f of A. What do you think I'm going to draw next? Say it again. No, not this time. Of course, the tangent, right? Okay, the tangent at P. Very good. Now, I have this point, A, f of A. Can anyone give us the slope of the tangent line at P? Yes, very good, f prime of A. So now here's what we have. We have one point, which is P, A, f of A, and we have the slope, which is f prime of A. And I would like us to find the equation of the tangent line, of tangent at P. Tell me what you're going to use and what we plug in. Is there a particular equation that you would think about? I think so. Is there a particular equation that is on your mind? Which one? Very good, awesome. Perfect. I do have the point A, f of A, and I have the slope f prime of A. Can anyone dictate the next step? allow me to, and I hope you will allow me to, replace y by what do you think? What do we always replace y by when we need it? Of course, f of x. Awesome. Very good. So can anyone put everything together and tell me what to write? And then I'll explain what this means. You will say f of x. Very good. Awesome. Equals f prime of a. Very good. Times. Of course, I'm going to solve for f of x. You're going to remember this when you talk about series in Calc 2. Forget about that for now. So, what does this mean? The correct symbol here should be approximate. Let me explain why and what it means. And you'll tell me whether you agree with this. And then we'll look at the problem. I claim that near A, not near A, but near A, very close to A. It doesn't matter whether I evaluate the function using the function or I evaluate the function and get an approximation using the tangent. At this point, it doesn't matter if I use near this point now. It doesn't matter whether I use the function to evaluate or this tangent to evaluate. And this is the equation of the tangent line. So if A is 5, and I use this line to find f of 5.1, or I use the function itself to find f of 5.1, it does not have a huge difference, a huge impact. I cannot use this line to evaluate the function at this point. It's too far. I would have to use this tangent line near that point. But near P, left and right, as close as I can, not too far away, I can evaluate the function using this or get a very good approximation using this. Why would I ever think of doing that? Because evaluating a linear function will always be easier than evaluating any function. And this is what we call the linear approximation of f of x near A, not too far from A. So let's look at a problem. If we have, if you're trying to, but still the slope will be 0, right?
Right. But is it like the approximation will be like farther off something like more?
No, it will be very close because we're not using the fact that its slope is 0. We are using the equation of the tangent line with the slope 0. Right? Very good. Very good question, actually. Thank you. Okay, so let's look at an example. So what this means is this. At any point on the function, we can linearize it, quote unquote. Meaning, we can determine the equation of the tangent line. Of course, the function has to be differentiable there. If it's not differentiable, there's no discussion, right? So it has to be continuous and differentiable. So at any point on a function that is continuous and differentiable, I can create the equation of I can find the equation of the tangent and evaluate the function using that new function, which is a line. Not just the slope, just the equation. Okay, so let's see. Okay, so there is a difference between the linearization, which is uppercase L of x, and the linear approximation. So let me write it because I put the symbol there, but I just want to make sure you understand it too. So this equals f of a plus f prime of a x minus a, and this is approximately f of a plus f prime of a x minus a. This is the equation of the tangent. This says that the function can be approximated by this. And you can say, why do we need two things? Well, sometimes we're asked to find the linearization. So this is called linearization. And this is called the linear approximation. If we can use the linear approximation to approximate the function, or we can find the function value at that point. Okay, so find the linearization, which will also be the linear approximation of the function at a. So choose any function. One, two, three, four. Which one? 4 it is. So that's x to 3/4. A is 16. So this is problem 4 on the same 255. Ready? So we're asked to find the linearization. So that is L of x, which is the equal symbol, right? F of 16 plus f prime of 16 times x minus 16. So first of all, I replaced a by 16 everywhere. Then f of 16 will be 16 raised to 3/4 plus, I have to find f prime. And once I'm done with that, then I put x minus 16. But I have to find f prime. Can anyone give us f prime of x? So 3/4 indeed. X. 3/4 minus 1, negative 1/4. Very good. Awesome. Great job. So this will be 3/4 and 16 raised to negative 1/4. And this is guaranteed to be a line. Yes, I have to clean it up. Yes, I have to present it in y equals mx plus b. So it's not done. But I just want to make sure, is this clear? Okay. So then, the 4th root of 16 is 2, and 2 cubed is 8. So L of x equals 8 plus 3/4. The 4th root of 16 is 2, but it's 2 to negative 1, which is 1/2. X minus 16. So then we have 8 plus 3 over 8x minus 16. And finally, I distribute. L of x equals 3/8x. 3 over 8 times 16 over 1 is 6. So minus 6 plus 8 will be positive 2. So my question is, if you want to find f of 15.5, would you really want to put 15.5 here? Or you will want to put 15.5 here, which is a line. You just multiply by 3, divide by 8, and then add 2. Right. So that's what it really means. At any point, you can find a function that is a line that approximates the original function near that point. Questions about 3/8 x plus 2? Questions? I know we have about 10 minutes left. What would you like to do? I don't want to start the last section. I only have 10 minutes to talk about the last section, and we can start reviewing from scratch this chapter. But I don't want to start a new section in the last 10 minutes. So what would you like to do? Would you like to choose another linearization? Would you like to go back to logarithmic differentiation, implicit differentiation, the chain rule, product rule, quotient rule, anything from related rates, anything that we looked at? Anything from the past or anything that we covered today? What would you like to work on? Okay, why don't we work on some derivatives since we have 10 minutes left? So let's work on a couple of derivatives from the review exercises, page 265. So for example, like problem 12, I'm going to copy a couple and let's work on those. Let's say number 12 on page 265, y equals arc sine 2x everything squared. So let's differentiate that. And also 28 on 265, which is y equals cosine x raised to x. So let's start with the first one. Per second, yes. Do we have an answer for the first one? I'm putting the attendance in. Do we have an answer for the first one? Ready? So y prime 2 arc sine twice x times, yes, 1 over the square root 1 minus squared, which is 4x squared, very good, times the inner function prime. Excellent, well done. So the final simplified, a little bit condensed, is 4 arc sine 2x, in parentheses if you want, that's fine, the square root of 1 minus 4x squared. Great job. Perfect. Okay, what about the second one?
Negative x cosine x.
It's a function raised to a function, and there is no formula. We have to, yes. It's better to make a mistake now than on the test. So that's good. So this is x times natural log cosine x. What now? Yes, 1 over y times dy over dx equals, remember this is function 1 and this is function 2. It's a product, which means when you differentiate, you have to have a sum of two terms. Please remember that. Okay, first function prime, 1. So natural log cosine x plus x times the second function prime. Very good. 1 over cosine x, but times negative sine x. So then dy over dx, we have to multiply both sides by y, which we have to replace by cosine x raised to the x power. And then we have natural log of cosine x minus x tangent x. I changed sine x over cosine x into tangent x. There's no need necessarily, but I just wanted to get rid of the fraction. Yes. Any questions on this? Any questions? Please, any questions? Are we okay with this? Okay, we have 3 minutes. Let me choose one more. From the same page. Let's look at, yes, 13. In 13 we have y equals e to 1 over x, everything divided by x squared. E to 1 over x, everything divided by x squared. Allow me to give you a hint on this. This is what I would do. But that's me. Doesn't mean that you have to do this. Do we understand what I changed and how I changed that? Yes? It's only because I think it's easier to differentiate. But you can say, nope, I prefer the ratio and use the quotient rule. That's fine too. It does not matter. The answer will definitely be the same. So when we find y prime, can anyone dictate? Remember, it's a product. Function 1, function 2. Yes, negative 2, x2, negative 3 times e to 1 over x plus, when we differentiate the product, we have to have a sum of two terms, plus x to negative 2 times, yes, e to 1 over x times this function prime, and we know, hopefully moving forward, we will not forget that that is negative 1 over x squared. Yes, I can clean it up a little bit. I will factor out e to 1 over x first to get it out of the way. I will also factor out negative 1 because both terms are negative, this negative and this negative. And let's see what is left. A 2 over x cubed is left, and a plus 1 over x to the fourth is left. And yes, I will factor out 1 over x cubed as well. So negative e to 1 over x cubed. And in parentheses, I have 2 plus 1 over x. And I will write 2x plus 1. So negative e to 1 over x, 2x plus 1 over x to the 4th. This is what I would recommend.